In this video, we will be introducing attention models for deep learning. In attention models, one focuses on small parts of the data in order to make more accurate predictions. Focusing on small parts of the data can be viewed as a type of regularization. As we'll see, attention models are very useful in many applications such as text or images, where one is often making predictions from small portions of the data. So in order to motivate the problem of attention, let us first discuss the biological motivation of attention. So since artificial intelligence tries to simulate biological intelligence, let us look at how human beings use their available sensory inputs in order to accomplish specific tasks. So let us look at a specific case where we are trying to find an address defined by a specific house number on a street. So an important component in this task is to identify the number written either on the door or on the mailbox of the house. Now in these cases, when a person is trying to find the number of the house, the whole image of the house and the entire scene falls on the retina. However, one rarely focuses on the full image. Rather, one often pays greater attention to the relevant portions of the image that will help the human being identify the specific portion of that image that gives him or her the specific number of that house. So this can also be associated with how the retina is structured. So typically the retina is structured in a concentric way where the central portion of the retina is referred to the fovea, and the fovea lies inside the macula, and the macula and the fovea, they contain the maximum density of receptors. Whereas most of the retina is really a peripheral vision which corresponds to the least density of receptors. And often when you are doing detailed tasks, such as for example reading a document or even listening to this presentation, you are using your macula and fovea to focus on the relevant portions of the image. Those are the portions of the image that is carried in high resolution to your brain. Most of the other portions of the image which are carried by the retina are not transmitted in high resolution to the brain, because for performing specific tasks, one only needs to process small parts of the image in greater detail. So how does the process work in human beings? For example, when one is trying to find the street number of a house. So what you want to really do is that you want to systematically focus on small parts of the image to find what you're looking for. And typically what happens with biological organisms is that they draw quick visual cues from whatever they're focusing on to identify where to next look to get what they want. So for example, if we first focus on the doorknob by chance, then we know from our experience, that is our trained neurons tell us to look to its upper left or right to find the street number. And the reason our neurons tell us to do that is because they were trained by past trial and error in order to look for the house number in that way. So the moment we talk about trial and error, we are suddenly talking about reinforcement learning. So many of the attention-based methods, they are paired with reinforcement learning methods, where there's an iterative process where the neural network tells where the neural network finds the portions of the image where to next focus on. And we will discuss one such model in the upcoming slides. So let's talk about this model, which we call recurrent models of visual attention. This model is a classification model. So it uses a relatively simple neural network for image processing. Now normally for image processing, one tends to use convolutional neural networks, but at least for the image processing part, the feature extraction uses relatively simple layers. But what it does is that it transmits only specific portions of the image that are centered at a particular location. And this location, as we'll see, we'll use a reinforcement learning type of approach where these locations of the image change from timestamp to timestamp. And the way in which these locations can change with time is as the model learns more about the relevant portion of the image, it selects a particular location in the image at a given timestamp, and that is referred to as a glimpse. And since we are doing this process over multiple timestamps, you need a controller. The controller essentially outputs what the next location will be at which you will transmit the high resolution of the image, as well as the prediction of the class label at that particular timestamp. So here we are looking at a classification application, although in principle it can be used for many different types of applications, such as image captioning. And uh, the choice of which location to look at in a particular timestamp, it is based on the feedback from the glimpse. So the neural network processes the glimpse in a timestamp, and then it gives feedback where to next look in order to get more informative feedback about the class level of the image. So let's discuss what the components of the neural architecture are. So the components of neural architecture are the glimpse sensor. So the glimpse sensor essentially creates a retina-like representation, which of the image xt, which is based on location lt-1. The glimpse network contains the glimpse sensor and encodes both the glimpse location LT-1 and the glimpse representation row XT LT-1 into hidden spaces. So this is a key image processing component, which is typically much simpler than a convolutional neural network. And then, of course, we have a recurrent neural network, which is the controller. So this recurrent neural network, it outputs two things. One is that it outputs locations for the next timestamp, where to next focus in the image, and also outputs an action at the current timestamp. Now, this action at the current timestamp depends on what application that you're looking at. So typically, for example, in an application like classification, it will just output the class label. So as the timestamps progress over time, its output class label, its accuracy is going to improve as you take more and more glimpses of the image. And the important result is that this relatively simple glimpse network, it is able to outperform a convolutional neural network because of the attention mechanism. So even though we are looking at a classification application which can be solved with a traditional convolutional neural network, what we are showing, what this paper shows is that even using a relatively simple network for processing an image is sufficient when you're pairing it with an attention mechanism. So here I have shown the neural architecture. So the overall neural architecture is shown on the right, whereas different components of neural architecture are shown on the left. So let's focus on the portion of the architecture on the right. So as you can see, at each time step, the input is the image. So it's the same image at each timestamp because you're trying to classify it, and it's a location. So you can see at the first location you have LT-1, which is the location. Then the glimpse network processes this image, and it creates a representation of the image, and then you have a hidden layer which again processes the image, and then you have an output layer which gives two outputs. So one is that it gives you the action at timestamp t, that is application specific. So for example, in image captioning, that action would be the next word in the caption, whereas in classification it's simply the current estimation of the class label. So it could be a simple softmax output telling you what the class label is. Now in the classification application, which is what we are focusing on, since you have an output in each timestamp, typically you would expect that as you take more and more glimpses of the image, your class label prediction is going to improve from glimpse to glimpse. As you can see, the location output, it becomes an input for the next timestamp. So this is a recurrent neural network where the output at a given timestamp is used for input in the next timestamp. And on the left, I have shown the glimpse sensor and the glimpse network. So top left is the glimpse sensor. All it does is that it takes a location and essentially it creates the retina-like representation of the image, which is essentially row of the image at a particular location. Row is the function which creates the retina-like representation. And then, of course, on the lower left, I have the glimpse network, which creates the representation of the image after passing it through a number of layers of the neural network. And note that the glimpse network contains the glimpse sensor. So here we use a reinforcement learning setting where the action corresponds to choosing the class label at each timestamp. Now, as soon as you have a reinforcement learning setting, you also need a way in order to decide the rewards at each timestamp. So the reward at timestamp t is 1 if the classification is correct after t's timestamp. So if the output at t is correct, then you give a reward at 1. And what you do is that you sum up discounted rewards over all timestamp, and it is common to subtract the baseline to reduce variance. So again, you can go back to the reinforcement learning lecture, because I won't go through the details of these of the reinforcement learning, what the baseline means or the discounted reward means. But essentially, you're giving a reward at each timestamp if the class label is correct, and then you sum up the discounted reward. This is a very standard type of reward and baseline setting, and the baseline is simply the average reward that you expect at each timestamp. And this was trained using a reinforcement framework, which is essentially policy gradients. And again, this is discussed in one of the earlier lectures. This entire framework is discussed in an earlier lecture. And this approach outperforms a convolutional neural network in spite of its relatively simple architecture within the glimpse network. Note that we are not using a convolutional neural network. The image processing part, its architecture is relatively simple. But by using between 6 and 8 glimpses, because of the approach where you are focusing on relevant parts of the image, you are able to perform very well with this type of setting. Now, one can also modify this approach for image captioning. So in image captioning, instead of using the glimpse sensor outputting location LT, which is a specific coordinate in the image, what you can do is that you can use L pre-processed variants of the image that are centered at different locations. So you create L pre-processed images which are centered at several pre-processed choices of locations in the image, and the reinforcement learning setting only selects one of these L actions. So it's a discrete output. And another of the output, which is the action at the next timestamp, is the subsequent word in the image caption. So in the classification application, your reward was based on the classification accuracy, and in the image captioning, your reward is based on the caption prediction accuracy. So here I have shown the work which is show, attend and tell, where it gives you the entire neural architecture. So again, you are using a recurrent neural network, which is essentially an LSTM with attention over the images. But here you are using convolutional feature extraction. So you do use a more complex neural network in this case, because image captioning is a more challenging task. And here you can see for an input image, it gives this caption, a bird flying over a body of water. So it gives you this word by word generation. Often what happens is that this word by word generation, the way it happens that while it's generating a particular word at a given location of the image, often it highlights a particular part of the image which is relevant to the word at hand. Now, in the image captioning, there were two types of attention that were used in this paper. One was hard attention, which selects specific locations, and this approach uses reinforcement learning because of hard selection of locations. And the other is soft attention, which gives soft weights to various locations. Now, here you don't need to use reinforcement learning, and we won't discuss this approach in the case of the image captioning setting, though you can go back to the image captioning paper. This paper is paper by Zhu et al. To see how they have used soft attention. But we will discuss a different approach. We'll discuss machine translation application for soft attention. And in the case of soft attention, the advantage is that you don't need to use reinforcement learning. You can use somewhat more conventional models. So here I have shown in the image captioning application where you had a bird flying over a body of water. Both for the hard attention and soft attention case, what the highlighted portions of the images. Now for the soft attention, larger portion of the image are highlighted because you are giving soft weighting to certain locations in the image. And you can see that very often the location that is highlighted is relevant to the word that is being generated. Next we'll discuss the application of machine translation. Now, we had discussed machine translation in an earlier lecture on recurrent neural networks, and we briefly discussed that model before we go into the attention model. We'll devote 2 slides to that. So, a basic machine translation, what it does is that it hooks up to recurrent neural networks, and typically an advanced variant like an LSTM is used. But here, throughout our lecture, we'll use a basic variant of a recurrent neural network for simplicity. Now, what an attention model does is that it focuses on small portions of the sentence while translating a word. And here, we'll be using a soft attention model in which the individual words are weighted. So this is the basic machine translation model, which is English to Spanish translation. I had already discussed this model in an earlier lecture on recurrent neural networks. So you can see on the left you have the first recurrent neural network which encodes the English sentence, which in this case is I don't understand Spanish. And the second part, which is second recurrent neural network, it outputs the words in the Spanish language. So here we are not using any recurrent network. You can see you have these hidden states. So the hidden states of the first network, you have a superscript of 1 on the hidden states. So you can see H1 which is a superscript which is telling that it's a source sentence. For all the source hidden states of the source sentence, you have a superscript of 1, and that is relevant for what we'll discuss in the next slide. So that's why I'm pointing out this notation. And for the target sentence, you can see you have a superscript of 2. So you have H1, 2, H2, 2. So for each position in the target sentence, you have a superscript of 2. And you can see the inputs are essentially x1, 1, that's in the source sentence, and then in the output and the outputs of the target sentence, they are y1, y2, y3, and y4. So in this case, your output is no entiendo español, which is basically a translation of this sentence from Spanish to English. So what does attention do? What attention really does is that the hidden states HT2, they are transformed to enhanced states HT2 with additional processing to form an attention layer. So what this attention layer does is that it incorporates context from the source hidden states into the target hidden states. So one of the problems with this particular type of model is that, as you can see in this network, this entire sentence is converted into a fixed length representation. So for example, when you are outputting the word entiendo in Spanish, you really should be focusing on the portion of the source sentence corresponding to the word understand. However, since you have already created a fixed length representation, when you look at the hidden state H22, which is outputting entiendo, it provides no special importance to that particular portion of the source sentence. The goal of the attention mechanism is that while translating, while outputting a particular target word, it wants to be able to learn what portions of the sentence to focus on to incorporate context. And it does that in this case by using a soft attention mechanism, by soft weighting of the different hidden states. So let's look at what we are talking about here. Now we are using a soft weighting of the different hidden source states. Let me clarify that. So this context vector, it is defined here. So you can see this, you have a dot product within the exponentiated bracket. So you're taking a dot product between the hidden state in the source sentence and the hidden state in the target sentence. So you're saying that if they are more similar, give it more weight. Now note that the denominator here is just a normalization factor. So here what you're doing is that you're taking all the source states and you're weighting with a value ATJ which is between 0 and 1, and all the ATJs, when you sum it over all the J's, so for a particular target, for position T in the target sentence, at a particular position T, all possible source positions, they have weights which sum up to 1, and each each hidden state in the source sentence is being weighted by ATJ. ATJ tells you how much for position T in my target sentence, how much attention do I pay to the location J in the source sentence. And this ATJ lies between 0 and 1. Now that creates a context. So that context is essentially a weighted representation of your source vectors. Now note that in your vanilla model, you only use the fixed length representation at the end of the sentence. Here what you're saying is that at different portions of the sentence, I am going to look at the hidden state and I am going to weight them with an attention weight, which is a fraction between 0 and 1. And after using this weighting, I'm going to create a context vector, which is your CT. So at position T in the target center, when I'm outputting, let's say at position 2, I'm outputting the word entiendo, I will have a context vector for that specific word. Now, what you do is that once you have this context, what you do is that you create a new target hidden state, HT2, which is enhanced with this information from the context. So now you have this new HT2, which is the tan WC CT HT2. So now it's both using the hidden state HT2, which you would always use, and it's using the context. So now this hidden state is more enhanced because you have also used this additional context. So now you can see that you have this new representation where you have added an attention layer. So as you can see this, you have an attention vector which I've shown here, A2, and that is used to create the context, and the context goes into the hidden state H22. So, and now note that this weight WC, it is learned. In equation 2, you have this weight WC, it is learned by using standard back propagation. So the attention layer also has trainable weights that it uses for the learning process. And the way in which it learns those weights is that over time, as you train it over many sentences, it learns based on the source and target pairs what portions of the source sentence to focus on. So what have we really achieved by adding the attention layer? What we have achieved is that the hidden states will be more weighted towards specific words in a source sentence while we are outputting specific target words. And the context vector, what it does is that it helps to focus the prediction towards the portion of the source sentence that is more relevant to the target word. And the value of the attention score ATJ while predicting a target word will be higher for relevant portions of the source sentence. Now, there are many variations of this basic model, and I have the citation for this paper in the next slide. So here I have given the variant. So what we just showed was the dot product model. So it uses simple dot products for similarity, but you can generalize it by using other types of similarities. So I have shown different forms of the similarity, different ways of scoring score TS, and then you can calculate this attention value. ATS is given by EXP score TS divided by, so this is the same equation that I had shown, the equation 1 over here. So I have shown many different variants for calculating this value of ATJ. So these different variants are shown in equation 3 over here, so that you can calculate the score TS in many different ways. Now for soft attention models, these variants don't necessarily help too much, but there are also some hard attention models discussed in that paper where these variants tend to help in terms of the accuracy. Now, there are more details of these hard attention models that are available in this paper. In fact, both the soft attention models and the hard attention models are given in this paper that I have listed in this slide. And these attention ideas, they have also been generalized to neural Turing machines. And that is also discussed in the book.